So where does all of that energy come from? Nuclear fission releases a lot of energy. Where does it come from? So here's the fission reaction for uranium-235. Uranium-235 plus a neutron, we're going to get barium-140, krypton-93, and 3 neutrons being emitted. So we learned in your previous class, Chem 1A, about the law of conservation of mass. So if we look at the mass of the reactants and the mass of the products, and we compare those, we've got 236.05258 atomic mass units in the reactants, 235.86769 atomic mass units in the products. And we're using correct indications of precision and sig figs and everything, and so this number is different than that. There is a loss of mass. What's happening in a nuclear reaction is matter is being converted into energy. So this loss of mass is real, and that matter that was lost became energy. So you've probably seen this equation before. E equals mc squared. One of Einstein's famous equations. Energy is equal to mass times the speed of light squared. So we could calculate the energy produced in the fission of uranium-235. So the first thing we have to do is figure out, well, what is the energy difference there? So I pulled up my calculator here, 236.05258 minus 235.86769. So the loss in mass is equal to 0.18489 atomic mass units. Do you remember what the speed of light is? 3.0 times 10 to the 8th. Yeah, 3.0 times 10 to the 8th meters per second. So if we square that, we're going to get meters squared per second squared. E should have a unit of energy. A joule is a kilogram meter squared per second squared. So the unit for mass we need to get from atomic mass unit to kilograms, right? That's not a number that I remember. It's not a number that I would expect any of you to remember either, but it is in the back of the textbook. Where'd you go? One atomic mass unit is 1.66 and a bunch of other digits times 10 to the minus 27 kilograms. So we can change this. One atomic mass unit on the bottom and 1.66 times 10 to the minus 27 kilograms. We could do this more precisely, but we don't need to, so 3.069 times 10 to the minus 28 kilograms. So the energy then is 3.069 times 10 to the minus 28 kilograms times the speed of light squared. Well, 2.8 times 10 to the minus 11, and that unit is joules. Is that a big number? No. But that's the amount of energy for one nucleus reacting. One uranium atom reacting. What if we had a mole? So if we want this to, this is 2.8 times 10 to the minus 11 joules per atom. If I calculate joules per mole, I have to convert atoms to moles. There's Avogadro's number of atoms in a mole. So we multiply this number by Avogadro's number. 1.66 times 10 to the 13. Joules per mole of uranium. You could put that in kilojoules, but it doesn't really matter. It's still, the number is way too big. That's a big number. Any questions?
It has, going back to the E MC squared, M has to be in kilograms, right?
To come up with a unit of joule, then the mass needs to be in kilograms. I mean, you could do it and end up with atomic mass units, meters squared per second squared, but you know, that's not a conventional unit. Any other questions?
The mass that you had originally, the 0.18,
Yeah.
that was just thought, like, per se we had that much.
That was looking at the difference here. The amount of mass lost when one uranium atom reacts.
Oh, okay.
Yeah. So I just took this number and subtracted that number.
Okay.
Yeah.
So the 2.8 times 10 to the minus 7 joules is 1
That was for one atom. Yeah. Let's look at a helium-4. If we look at the masses of so the way we're looking at this here is taking two hydrogen atoms, that's a proton and an electron for each of those, and adding two neutrons. If you put all of those together, you've got the components of helium, helium-4. So we can take the mass of the two hydrogen atoms, the mass of two neutrons, add them together, 4.03298. The actual mass of the product is 4.00260 atomic mass units. So mass has been lost, right? Where did the mass go? It's created in energy. So this is called the mass defect. And it exists in all stable nuclei. And that's why the numbers don't add up the way we would expect them to. You look at, uranium-235, and you look at the number of protons and the number of neutrons, and it doesn't add up to the actual molar mass of that atom because there's this mass defect. So when an atom is formed, some matter is lost and it is transformed into energy. So that energy is called the nuclear binding energy. It's the amount of energy required to break apart the nucleus into the component nucleons. And remember, nucleons are referring to all the particles in the nucleus, primarily protons and neutrons. So the nuclear binding energy is an energy, and so it can be reported in different units. Nuclear physicists often use the unit electron volt. So an electron volt is the kinetic energy of an electron that's been accelerated through a potential difference of 1 volt. So they call it an electron volt. It's a very small quantity of energy. a mega electron volt is 1.6 times 10 to the minus 13 joules. So a mega electron volt is in that range, because what was this number here? This is minus 11 joules for one atom. So this is a reasonable sort of unit when measuring nuclear binding energy of single atoms. And just for reference, an atomic mass unit is equivalent to, that amount of energy is equivalent to 931.5 mega electron volts. So electron volt is just a different unit of energy. And that is a conversion factor that could be useful. You don't need to memorize that, though. If you need it on the exam, I'll give it to you. Okay, so we can do a calculation like this. The mass defect for helium-4 is 0.03038 atomic mass units. What's the nuclear binding energy? Well, the simplest way to do this calculation is to use the nuclear physicist's unit of electron volts. So one atomic mass unit is 931.5 mega electron volts. So I'm going to do it that way. You can also take the atomic mass unit and use Einstein's E equals mc squared, convert the atomic mass units to kilograms and the speed of light in meters per second, and end up with joules. And then if you needed electron volts, you could use this relationship. But I'm just going to use this guy right here, 931.5. That's not what I wanted to do. So 0.03038. 931.5 mega electron volts per one atomic mass unit. So 28.30. Mega electron volts. So that's the nuclear binding energy for helium-4. You can compare that nuclear binding energy as a ratio of binding energy per nucleon. So for helium-4, it has 4 nucleons, so you would divide this by 4. And then you can compare the binding energy with different atoms, different nuclides, and we see that a larger binding energy equates to a more stable nuclide. Okay, so in this problem we're asked to calculate the mass defect and nuclear binding energy per nucleon for uranium-238. So uranium-238 has a mass of 238.050784 atomic mass units. Did they give us all the numbers we need here? No, they didn't. How do we calculate the mass defect? We're going to have to add up the components, right? So uranium-238, atomic number is 92. So the components here are protons, neutrons, and electrons. How many protons? 92. So 92 protons times the mass of a proton. Well, that's given in the book as well. It gives both atomic mass units and kilograms. Since we're doing mega electron volts, let's use atomic mass units, and then we can just use that nice little conversion factor. So the mass of a proton is 1.00727 .647 atomic mass units. Double checking that I wrote that down right. When we're subtracting here and we have all these decimal places, we want to definitely use all the decimal places we can. How many electrons? 92. So there's 92 electrons. They are small, but we can't forget about them. Mass of an electron, 5.48, 579909 times 10 to the minus 4 atomic mass units. That's a 4. And then, how many neutrons do we have? Yep, 238 minus 92. 146. That's a lot of neutrons. So plus 146 times the mass of a neutron, which is 1.00866,492. So I hope somebody else is doing this too. 239.984989 atomic mass units. 2468. 246. Okay. So that is the expected mass if you're adding up all the components. And usually, like, when you're building something and you add up the masses of the pieces and you put them together, the overall thing weighs the same, right? That's what happens with large objects. But here we put these components together and they weigh less. They actually weigh 238. That difference is the mass defect. So the mass defect equals the predicted mass, the mass of all the components, minus the actual mass of the atom. And we don't do this with average masses, we do this with individual isotopes. So I've got that number I calculated, and I'm going to subtract 238.050784. $1.9341989112. Atomic mass units. We're going to be limited here by the number of decimal places on this guy, so 246, 246. So the mass defect is 1.934199 atomic mass units. And then to calculate the binding energy, we're going to take that number and use the conversion factor to convert to mega electron volts. So that comes out to 1802. 1802 mega electron volts. Any questions? Yeah.
So the mega electron volt is just another unit of energy.
It's another unit of energy.
Could we potentially find it in joules?
Yes, you could do it in joules.
We could do like the E equals mc squared from the atomic mass.
Yeah, you could use E equals mc squared, or you could use the conversion relating mega electron volts to joules. There's multiple ways you can get there.
And the like the energy for mass for A and U doesn't change varying from element to element, or because an atomic mass unit is just like the weight of
An atomic mass unit is the same for everything. Yeah. Is this really the answer to this problem? No. I calculated the binding energy for one atom, but I need to divide it by the number of nucleons. How many nucleons? 238. So 1802 mega electron volts divided by 238 nucleons. .570. Mega electron volts per nucleon. That's what they asked us for. Any questions? It's hard to compare just the actual binding energy because all the atoms are different sizes. By dividing by the number of nucleons, then you can compare those across different atoms. The binding energy per nucleon hits a maximum at a mass number of 60. So that's in here. When you break heavy nuclei into lighter ones, that's exothermic. Combining two smaller nuclei into a heavier nucleus is also exothermic. So both of these processes release energy. When you take the uranium-235 and break it into barium and krypton, you're breaking it into atoms that have higher binding energy per nucleon. And the same when you're combining smaller things together. Any questions?